Bonjour, bienvenue à ce nouveau webinaire qui va traiter aujourd'hui des évolutions en termes de développement et process de développement et l'intégration de l'approche DevSecOps dans les développements embarqués. Aujourd'hui, je serai accompagné de Rob Dalton, qui est ingénieur d'application senior au sein de CodeSecure et qui vous fera la présentation principale. Et moi, je serai votre modérateur, donc je suis Frédéric Maraval, ingénieur produit et responsable produit au sein de la société Easit. Alors pourquoi parlons-nous du DevSecOps aujourd'hui? En fait, c'est essentiellement lié à l'évolution des développements, des logiciels et des équipes. Sur ces dernières années, il y a eu une très forte évolution. On est passé de projets ou de logiciels, d'applications logicielles relativement simples ou à complexité assez réduite, voire moyenne, généralement avec des équipes de développement plutôt à taille humaine et centralisées. Et sur ces dernières années, on est allé vers des complexités de logiciels de plus en plus élevées et surtout des itérations très importantes durant la phase de développement, de déploiement et dans toute la gestion du cycle de vie des applications et des logiciels. Et les équipes ont évolué également avec une taille d'équipe de plus en plus importante et de plus en plus distribuée, voire délocalisée. Et toutes ces évolutions ont amené des nouveaux challenges dans les phases de développement et notamment dans les phases de test des logiciels. Et le but un petit peu de ce webinaire aujourd'hui, c'est de montrer dans toutes les évolutions, notamment des cycles DevSecOps, comment les outils ont également évolué, notamment l'application des outils de type SAST dans ces approches-là. La main à Rob Dalton qui va vous faire la présentation globale de l'approche DevSecOps et des outils SaaS. Rob, I give you the right for presenting and it's up to you.
Lovely. Thanks very much, Fred. Okay, hopefully you can see my desktop now. So thanks for attending, everybody. As Fred said, my name's Rob Dalton. I work for CodeSecure, a partner of Easit. What I want to talk about today is how to deploy our static analysis tool, CodeSonar, into CI automated environments, which is and has been a growing requirement and a need for a number of years now, or basically automating the deployment and usage of static analysis tools. I want to spend the majority of my time working you through a typical deployment of CodeSonar and how a developer would be interacting with CodeSonar in their IDE and then GitHub as the CI tool in this particular case. Through the end-to-end process of the developer experience. And then just follow that by highlighting some of the capabilities of CodeSonar as a static analysis tool, why it's good at what it does, why it's particularly a valuable and capable security analysis tool, which fits very well with the sec part of DevSecOps, which is the fundamental idea behind CI environments. And then round off with some questions afterwards. So in terms of use case, historically, code bases were smaller than they are today, and that tended to imply smaller teams of developers working on those code bases, potentially in single locations, and not particularly many tools used during the development process as part of the tool chain. Perhaps just somebody working with an IDE at best, and running tools like make perhaps manually or as cron jobs. Very, very simple environments amongst the few developers involved in that particular code base. What we're seeing much more frequently, however, these days is as obviously code bases are getting bigger to provide the capabilities and features that software needs to exhibit today, that obviously incorporates or demands bigger teams of developers, which, because of the network connected world that we live in these days, those developers can be anywhere in the world, literally, but still working as part of a closely knit team. And that also all tends to imply much more complex tool chains, not just the compilers and the IDEs, but obviously the CI environments that we're focusing on today, but bug tracking systems such as Jira, Git, of course, and many other common tools which can be part of that connected experience that the developers are used to these days. So a simplified visual on how that modern developer and environment may look is we've got the developers in the potentially disparate locations on the left here, working in potentially some IDEs, Eclipse, VS Code or Visual Studio, for example. There are many others, of course, and they will be working on snapshots, branches of the code on their local desktops, and potentially periodically submitting those code changes and those branches that they've been working on through to the CI environment that they're connected to, such as GitLab, GitHub, Jenkins, certainly 3 popular C environments that we at CodeSecure see amongst many of our users. That particular tool itself will most typically these days be connected to Git as the code repository, but there are other choices as well. And these will be the fundamental elements that you will see necessary to support the modern collaborative development amongst the army potentially of developers which may be working on a code base these days. So what I want to show you really today is how CodeSonar can be added into that environment, so that it's not necessarily the in-your-face tool that it can be and was more so in years gone by when environments were much simpler. In the more CI-centric environments that we see CodeSonar deployed into today, CodeSonar becomes more of just an automated piece of the execution, and is quite a hidden piece of the execution, and really only manifests itself in the places that the developers and the team in general want to actually consume CodeSonar's results, which is obviously in the IDEs that the developers are working in, but can also potentially be in the CI native interfaces themselves, as I'll show you a little later on in my demo. So what I have chosen for my demo is probably 2 of the most popular environments that we come across today in terms of IDE. That would be VS Code from Microsoft, and also from Microsoft their GitHub CI environment. And I'm going to show you the workflow from cloning the code base into the IDE through to working on a branch of code in the IDE, triggering a merge request, and then seeing how all that behaves and what we needed to add into a typical CI pipeline to add CodeSonar and to have CodeSonar perform an analysis and do other interesting key activities that we find many of our users like to make sure CodeSonar can do in those pipelines. And then obviously the final step in that sort of workflow will be, once the merge request is completed and the analysis has been performed, pulling the static analysis results findings back into VS Code where the whole process started. So let me just bring up VS Code here. So, well, actually, let me start off, sorry, in my view of GitHub. As you can see here in GitHub, which I'm using in the cloud in this case, I've got my project which we're going to work with. We can see this project here actually comprises a number of different languages. There's some C and C++ in here, but there's lots of Kotlin and Rust and Python and JavaScript, all languages which are capable of being analysed by CodeSonar, though that's not the main thrust of this presentation today. And the first step to analysing, or any developer working with this particular code base, would be to take a clone via this URL, for example, here. So if I pop over into VS Code, I've actually already cloned the code base here. We can see all of the different directories which are nicely organised by language for the most part. We can see I've got some C++ source files already open here, and actually I've gone a little further. I've already created a branch here which happens to be called Tuesday in this case, and I made some code modifications here which I've already published into back to my GitHub repository here. So if I switch back into my repository, and we will see that I've got 3 branches here. There's my Tuesday branch, and I have already triggered the pull request on that to execute the pipeline and perform the static analysis. And in a few moments, once I've walked you through that pipeline script to see how we integrate and deploy CodeSonar, I'll move over to the merge request summary and show you how that looks as well. So let me first take a look at the pipeline code here, and a large proportion of this code is just your typical script execution steps that you would have here for building your code anyway. Worth pointing out that whilst this is quite a GitHub-centric presentation, we can do equivalent things for a variety of other CI environments, notably GitLab and Jenkins, but frankly it could be any CI environment, Azure or Bamboo from Atlassian. It doesn't really matter, because the core initial and key step that you need to do to literally perform CodeSonar static analysis in your pipeline is to somewhere embed a call to running CodeSonar, as I've done here. Clearly, CodeSonar here is a parameter, which if we scroll up, you can see it's actually just running CodeSonar in this particular path. Where is this binary? That's an interesting question itself. Well, that CodeSonar binary, the analysis execution engine itself, is part of this Docker container. So in other words, it's entirely possible to build a Docker container containing not just your development tools, which is the key step that many of our users will do these days when setting up CI pipeline scripts. They'll build a Docker container containing all their deployed, all their necessary binaries, their development tool chain, for example. And obviously the reason why that is preferred these days is to be able to have that clean, reproducible build environment where the pipeline will execute, the pipeline environment will set up, download and set up the Docker container within that environment, providing all of the development tools and so on. The code will be built, and then once the pipeline completes, the whole working directory behind the execution of that pipeline is deleted, and then next time that the pipeline executes, it always starts afresh. So that desire to have that clean, reproducible environment is well supported by by the idea of Dockerizing binaries, and CodeSonar could definitely adhere to that model as well. So if we scroll down the pipeline script, there's some bits and pieces to do with setting up security and authentication, which I won't dwell on, but suffice to say, CodeSonar can be executed in a secure manner only by environments or users that have the necessary privileges or credentials to be able to execute it. But as I said earlier, the key step to adding CodeSonar to any CI pipeline is just running the CodeSonar an analysis command directly, and in this particular case, around the compilation of a couple of my C++ source files here. Further on down the pipeline script, we can see the evidence of how CodeSonar is used to analyze, in this case, Python, or analyze Rust, or analyze Java, or analyze JavaScript. So just highlighting how CodeSonar is a multi-language static analysis tool. The final language which is analyzed here is some Kotlin sources by this particular command here. So all of those individual commands are analyzing all of the different language subsets in my entire code base here. And then once that analyses have completed, we then follow on to another popular step that organizations typically want to conduct, and that is collecting key metrics post-analysis that are then used to trigger conditional other behaviors in the pipeline. And the common one is how many results did the analysis find, and if there were more than a certain number of results, for example, potentially terminating the pipeline script. There's no point going on to the continuous deployment phase of the pipeline script if you found too many static analysis warnings, for example. Or another key metric in a similar vein which users are interested in is, were there any new warnings in this particular analysis compared with a particular baseline analysis? And if there were any warnings in that diff result set, then again, potentially use that metric to conditionally terminate further execution of this pipeline. The point I want to make is that post-analysis, it's entirely possible to query and look for any particular metric that is relevant to your interests and needs. And this particular command here is just one example of performing that to get hold of all of the new warnings in this case, as you can see from this argument here, and then passing a list of warnings, the new set of warnings which is returned by this command, and in this case passing them through the Unix WC command to get a count of how many warnings were on that list, and then the value is assigned to this new count variable, which I don't do anything with in this case, but you can see how straightforward it is to collect that metric, which we could have then added some code to this pipeline to do those conditional activities as I described earlier. Following on from that, we run a similar CodeSonar command here to obtain a list of all of the warnings as a SARIF file, which is a very interesting thing to just briefly explain. SARIF is a particular file format for expressing static analysis warnings in. It's a standard which has been adopted and supported by a number of organizations in the static analysis space, but Microsoft themselves are also a large player and supporter of the SARIF format as well. And as such, GitHub itself, the CI tool I'm using here, can ingest SARIF formatted static analysis results, which we take advantage of in a moment, as we will see too is true for VS Code when we complete this developer experience. But in this particular case, we get a dumping of all of the results found as a SARIF file, and then following that, we upload that SARIF file to GitHub, as can be seen here. And we'll show, as I say, in a few moments how that presents itself in the merge request summary page. And then following that, there's a further summary that we can post into the GitHub merge request summary page via this command here. I'll show you again how that manifests in a moment. So the key takeaway there is just to show you how you would go about incorporating CodeSonar and different activities into your pipeline script. This particular capability here, publishing the SARIF file to GitHub, is only viable for GitHub Enterprise editions. Similarly, we have an equivalent capability for GitLab Ultimate editions as well. Whereas this particular summary that we can publish here is suitable and available for all flavors of GitHub and GitLab. Okay, so clearly I've not ran the pipeline here, but I've previously ran it. So if I come over to the pull request page here, we can see the evidence of the extra decoration which has been added to the pull request page as we talked about in the CI pipeline. So what we see at the top here is GitHub's own representation of the SARIF warnings which we uploaded to GitHub. And GitHub does rather a nice job here of posting those findings. And in this particular case, it's summarizing one of the potential issues which was discovered here, which was an empty if statement. And it shows the code modifications that comprise that particular problem, which was one of the code modifications I made in VS Code when I then published the code up to the CI environment. And we can click on show paths here, and GitHub has this quite nice step-by-step presentation that it shows with comments lifted from the SARIF file aligned with the lines of code where these comments apply. So it's rather a nice attempt to annotate the source code so you can understand how the occurrence of this relatively simple issue in this case of an empty if statement, as you can see. So that particular decoration is only available for GitHub Enterprise editions into its security analysis report. But for all iterations of GitHub, CodeSonar is able to produce this results summary, giving you a count of the how many high, medium or low severity warnings there were across all of the code which was analysed, so the Kotlin, the JavaScript, the C, C++, and so on. And further down below here is a summary of the top 10 warnings by warning class. So there was 48 indent errors in our JavaScript. There were 10 explicit iteration loop warnings in our Rust code, and there were 7 different examples of spread operator problems in our Kotlin code. You may notice that these are all links, which if I were to click on would take us through to the information on each of these in our CodeSonar native web interface, which if I click through to at the moment, so I'm connected to the CodeSonar interface here. Let me just sign in, and here's the analysis that was executed by my pipeline previously. I can dive into it and review all of those warnings in here. There's over 300 of them, and it spans all of the different code warnings, you know, Kotlins and C and C++ and Rust and JavaScript and so on. All of the result sets for all of the different languages housed and homed in one particular format. So just to close the developer experience, if I go back to VS Code here now, we've got a plugin, a CodeSonar plugin for VS Code, which allows us to VS Code to interact with the CodeSonar repository that has stored all of our analysis results, and we can interact quite easily through the command palette option here, where we can either download all of the warnings for the analysis, or just the new warnings in the analysis compared to some arbitrary other analysis. So in this particular case, I'm going to download all of the analysis warnings. And what happens is that our plugin in VS Code goes off and queries the CodeSonar repository for the project in question, and it's seen that there's just one analysis actually in this particular case that belongs to this particular project. So if I click on that, our plugin in VS Code reaches out to the CodeSonar repository and requests as a SARIF file all of those warnings which were found in the analysis which were conducted, where I then have to save that SARIF file somewhere, which I'll just do that and replace the copy I already had. And what we see here then is this Microsoft SARIF viewer, which is another plugin which I have in my Visual Studio IDE here, and it shows us all of the information contained in the SARIF file, either showing where all the warnings occur by source locations, or indeed ordering all of that information by warning class. We can see in here, for example, there were 5 resource leaks discovered. So if I expand that row, we're now presented with each of the 5 resource leaks by their containing source files and line numbers where those problems manifest. And if I click on one of the issues here, you'll immediately see the source file in question pop into view into VS Code. And then below here, we've got all of the analysis steps with all of the commentary along the execution path. And you can see that commentary has been decorated directly into the source code view as well. So as I click on each of these steps, then the lines of code, if you can notice, are highlighted as I click on these comments here, are highlighted so you can see immediately where these comments apply. So obviously this first comment is highlighting how malloc is a recognized allocator which is allocating a resource of interest which is central to understanding this particular pointer, and the next line is telling us how pointer now reference as that resource of interest, and the next comment is telling us how string copy has no significant impact on our allocation here. And if we step further along the execution path, if I click here, then we jump into the go and use routine, which we can see is eventually invoked. And within the body of this routine, we've skipped a number of the steps here, but each of these are highlighting how the analysis took a particular branch through this conditional executing piece of code here, and the step I just highlighted here is now showing us how the analysis is saying if we take true path through this particular if statement, and it's now telling us why, therefore, this particular problem is basically occurring, because if we take the true path through this if statement, then we have failed to free the pointer of interest in this particular case, and hence the final concluding comment is highlighting why our resource of interest is going out of scope when we exit out of the go and use routine, and hence we've lost the reference to our allocation and therefore have a resource leak. So that's an example of a couple of tools that CodeSonar could integrate with, VS Code and GitHub in this example, but we could have done a similar demo for other IDEs that CodeSonar supports, Eclipse and Visual Studio, or the other IDEs, CI environments that I alluded to earlier in my demo as well. So if I go back over to my presentation here, I just want to briefly talk a little bit about actually why you would want to consider deploying CodeSonar anyway, not just how well we can deploy in CI and IDE environments. Well, CodeSonar's got a pretty powerful analysis engine, which I'll walk through in the following slide. As we will also see in those following slides, more information on the detailed warning commentary. But beyond that, CodeSonar provides its own triaging capabilities for annotating warnings, whether they're true or false, for example, has abilities for doing analysis comparisons as well, as I alluded to earlier. And besides that, we've got support for a number of recognized standards in the safety domains, such as MISRA and AutoSAR, for example, or in the security domains for conducting security analyses, such as SANS CWE Top 25 or OWASP. And I'll show you a sample warning which falls under those domains in a few moments. We have functional safety kits and qualification kits if you're working on code bases that demand those requirements of you, such as ISO 26262, in functional safety certifications. CodeSonar is pre-certified for working in that particular vertical, and if you're working in sort of the aerospace vertical, such as DO 178C, we have a qualification kit available for allowing you to qualify and certify the deployment of usage of CodeSonar for projects in that space as well. As I've mentioned a few times, besides the core languages that CodeSonar has been able to analyze for many years now, which are C, C++, C#, and Java, we can also analyze the languages which you see alluded to here. There's a whole range of metrics and reports that you can extract and tailor exactly to your needs as well. We have a whole host of toolchain integrations, which has obviously been the major point of the presentation up to now. And we're quite proud of our well recognized, or highly recognized, I should say, technical support that we can offer to our prospects and customers to make sure that their experience at CodeSonar goes very well. So what sort of key characteristics should you really be caring about if you're wanting to deploy static analysis? I won't spend too long on this because it's just sort of a bit of an addendum, but I think it's certainly worth defining because not all static analysis tools are equal, that's for sure. The primary capability of advanced static analysis tools such as CodeSonar was initially for finding all of the easy, undefined behavior edge cases that could be fallen into when doing C and C++ development. Those languages were sort of attempt one following assembly language almost to create more human readable languages, and that was the primary driver behind implementing certainly C, but also C++ to an extent. But those languages weren't memory safe, and they weren't well defined, and as I say, very easy to fall into many of the classical problems which static analysis tools are invented for, such as memory leaks and buffer overruns, and null pointer dereferences and uninitialized variables. These are all undefined states which are very easy to fall into in those two languages. But to be able to do a thorough job of finding these problems, then a static analysis tool needs to understand the semantics or the intent of what your code is getting up to, not just understand the syntax, and be able to have that precise and high quality semantic understanding requires that a static analysis tool builds a number of different representations of your code quietly in the background. Of course, you're not exposed to all of this behavior as the analysis runs, but CodeSonar certainly builds all of these representations or models, as you can see visually in the charts on the right here. And it's all right having this precise modeled and different representations of your code, but you need the analysis to operate in a precise but also a timely manner as well. We don't want an analysis producing a poor quality of analysis, but it's got to be able to do it in a reasonable time frame. And CodeSonar, I'm happy to say, can deliver on that requirement. It follows a particular mathematical approach to conducting the analysis called abstract interpretation. It's a technique that you can go and Google if you wish to understand, but basically it's a method which aims to maintain the precision during the analysis, but the interpretation part of the name here refers to how the analysis is realistic about how it deals with some of the more time-consuming aspects that static analysis tools can fall into as traps, and how to avoid those time-consuming traps and still be able to do a good job in a reasonable time frame. And then a very important part that your static analysis tool ought to deliver on, and is easily overlooked, but is something called API awareness. And you'll see that expressed very well in the example that I'm going to show in a moment. So if you've not got those characteristics which I've just walked you through, then you're likely to find yourself with a static analysis tool that is only able to find syntactic type problems in your code base, which tend to mean simplistic problems, only surface level properties, maybe single line or only problems that span one or two lines in your code base. And these are very simple problems that people can instantly agree with. It's very easy to find these problems as true positives because they're such simple problems, they're unequivocal problems. But the problems with these issues that syntactic analysis engines are only capable of finding is that they're not really ever aligned with the more serious defects which can occur in your code base. And again, I'll show you what I mean by that in a moment. Whereas if you've got a tool such as CodeSonar, which has all of those different strengths to how it conducts its analysis, then besides the syntactic simple problems that CodeSonar can find, CodeSonar is also able to find the problems that are more high value, the data flow and control flow sensitive problems that may exist in your program code base as well. And these align with the more high value serious defects as you see listed there, the null pointer dereference, and also the security vulnerabilities as well. So here is a rather a nice example which I just want to quickly walk you through which highlights all of those different capabilities, the API sensitivity and the control and data flow sensitivity as well. And this is a security vulnerability, a command injection problem. And we're finding more and more that this is a domain of problem that prospects and users are more and more interested in employing static analysis for. As I say, static analysis was originally invented to find those undefined problems in C and C++, and then as time progressed, a new capability was added to the armory of static analysis tools, which was looking to conduct safety analyses such as required by MISRA and AutoSAR and JSF type standards. But the security use cases, the growing angle that we're finding customers and organizations are interested in, obviously correlating with how much more network connected code bases can be these days, which obviously exposes those code bases to abuse by bad actors, to the hackers out there in the wide world, and untrustworthy governments, and all those different places that your programs can be exposed to in a network environment, and wanting to make sure that your programs are more capable of dealing with those threats. And that's what I mean by conducting a security analysis. So this particular command injection problem here, as I say, it highlights many of those capabilities that a tool such as CodeSonar is able to discover. This problem was found in an internet relay chat daemon, a public domain code base. The issue has long been fixed now. It's a nice example, as I say. And it starts off by CodeSonar recognizing that this rec-v call is a particular example of an API which pulls data in this case from a network connection into the program. And that is why the rec-v call is underlined in red. And CodeSonar is sensitive to a whole range of APIs in C, C++, Java, and C#, which are responsible for connecting your program to the environment, such as the network, or files, or environmental variables, or arguments passed to your program, and the whole range of APIs which are responsible for connecting to these different types of environment. CodeSonar is sensitive to them. So it knows, hey, rec-v pulling data over a network into your program. And correspondingly, therefore, read buff, the length parameters here are populated by that information or are touched by that information coming from the environment, which is why those variables are also underlined in red. Your visual cue that these are things connected to the environment and data from the environment. And then there's a highlighted execution path that the analysis took through this piece of code, as highlighted in the brown background color here. And we can see how along the execution path the variables maintain their red underlining. And if this in this particular piece of code, if these variables or indeed pointers had been aliased or assigned to other variables and pointers, then CodeSonar would have recognized that and would have underlined those variables and pointers in red as well, indicating how they were transitively connected back to the origin point of where this data got into the program. And then further along the execution path, we can see how that data, or this genuine backdoor, I should say, was added into this chat daemon code base by this innocent looking macro called debug mode 3. We can see that it's a piece of conditional code with a preprocessor definition, and when the code base was built with debug mode 3, obviously this code is part of the code base, and CodeSonar recognizes that and analyzes the code as protected by this macro here. And we can see that within the body of code which is conditionally compiled, that there is an attempt to check what has been received in the buffer, and if it compared with debug mode 3 info, which was in this case, it's not shown on the screen, but was just an arbitrary string, and because we took the negative check on that mem compare here, it basically meant that whatever was flown over, it basically meant that this test always passed, by the way. So all of this is an attempt to obfuscate real malicious intent on the code which was added here. So this logging macro was always executed, whatever was passed over the network connection. Debug log 3, we can see CodeSonar knows was actually a further macro called debug 3 do log system, which itself was a further macro which on expansion was the system API call. Okay. And so the big problem here, the big risk is that if this relay chat daemon was built and was running on a machine, an abuser knows that they could just connect to it and send a string such as, for example, rm-rf, which if you know your Unix or Linux would mean that this chat daemon would try and execute that rm-rf command here, which could have catastrophic repercussions, or they could have been executing something like an echo command to try and echo contents of a file and see if they could get sensitive data shared back to the abuser that way. Who knows what command they could have tried to execute, have executed by the chat daemon here, but you can imagine all of the possibilities and therefore the worries of this genuine backdoor which was added. And what is interesting about this problem that I'm showing you here is it's a security problem, but it's a high value security problem. To be able to detect this, you need an analysis which is aware of the routines which ingest data into your program, the routines which utilize and potentially do something dangerous with that data as received. And then the execution path, which you see outlined here in the brown background color, and how CodeSonar is sensitive to taking branches through that body of code, highlights how you need a static analysis tool which is both data and control flow sensitive. So all of those characteristics that CodeSonar has had almost since its, well, indeed since its inception as a static analysis tool, lend themselves very well to finding and presenting security vulnerabilities within your code base. Okay, I think I'll skip, in the interest of time, the CodeSonar user interface portion of my presentation. We've only got a few minutes left here. So I'll just round out my presentation just by drawing your attention to how we are quite proud of our support environment. So we don't just hope that you buy CodeSonar and then have the worry of how to execute and configure it and deploy it on your own. We're very available to you to help you accomplish all of those activities that you need to properly deploy and get best value out of CodeSonar.